And in this story, we have two primary goals. Our first goal is to get the amine in, and our second goal is to get the water out. Hey, OChemNinjas. I'm here today to talk about the imine formation. The imine formation is a reaction of an aldehyde or a ketone with a primary amine or ammonia to create an imine as our product, with water as the byproduct. That's what my drawing convention means here. This carbon/hydrogen means that it could be a carbon chain to be a ketone, or it could be a hydrogen to be an aldehyde. Same thing with our amine. We need at least two hydrogens on the amine, but that third group could either be a carbon chain for a primary amine or a third hydrogen to be ammonia. Since this is a reaction using a carbonyl as a starting material, it follows our story of the carbonyls. If you're not familiar with the story of the carbonyls, watch my video I have linked down below. It's a good overview, a good way to organize your carbonyl reactions. And in this story, we have two primary goals. Our first goal is to get the amine in, and our second goal is to get the water out. We need to keep these two goals in mind as we go through the mechanism to make sure we're staying on track. This carbonyl mechanism involves a neutral nucleophile, so we need an acid catalyst to facilitate the reaction, and that acid catalyst we typically use is typically a weak acid, typically something like acetic acid or pyridinium paratoluene sulfonate, PPTS. These acids have a pKa of around 4 to 6. A carboxylic acid has a pKa around 4 to 5. The pyridinium salt has a pKa of around 5 to 6. This is the sweet spot for this reaction. The mechanism for this reaction isn't quite as straightforward as you might think, so let's dive in and take a look. Much of the ambiguity happens here in the beginning of the mechanism. In a reaction with a neutral nucleophile, the neutral nucleophile typically does not have enough inherent energy to directly attack the carbonyl. Can a neutral amine directly attack a carbonyl? You can make a pretty good case that it does. Neutral nitrogen is more nucleophilic than you would otherwise expect, so there's a good case to be made that it can directly attack the carbonyl. Others might say if that's the case, then we might not necessarily need an acid catalyst. I'm not really here to solve that debate right now, so we're going to continue with the traditional story of the carbonyls with a neutral nucleophile. In the mechanism with a neutral nucleophile, it typically doesn't attack directly. Instead, the first step is typically the nucleophile picking up the proton from the acid catalyst. And so we'll do the same here. The neutral amine will react with the pyridinium salt to form the protonated nitrogen intermediate. As with other neutral nucleophiles, we do this not really because we want to. In fact, it actually makes it a worse nucleophile. We do this because we have to. Statistics. The solvent is statistically the most abundant thing in solution, so when we add the acid, the most abundant thing it's going to react with is the solvent, and so we protonate the solvent first. This is an acid-base reaction, so it's in equilibrium, and this equilibrium favors the products. The starting acid has a pKa of around 5 or so, and the product acid has a pKa of around 9 or 10, so the product side of this equilibrium will be favored. Next, we'll transfer that acidic proton to the carbonyl. Using the lone pairs of electrons on oxygen, the oxygen will act as a nucleophile and pick up that acidic proton to protonate the carbonyl and form the next intermediate. It's important to recognize that this intermediate is resonance stabilized. This step is also an acid-base reaction, so it's also in equilibrium. And what's very interesting here is that in this case, the equilibrium actually favors the reagent. The protonated nitrogen has a pKa of around 9 or 10, and the protonated oxygen has a pKa of around -3 or 0 or so. So the weaker acid wins, and that would be the protonated nitrogen. We don't see a lot of reactions where the reagent is favored. That doesn't make a lot of sense. We should be moving forward in the mechanism. But that's how the pKa's work out for this situation. And that's why the beginning of this is a little bit complicated. And ultimately, it doesn't really matter which order these steps happen in. This proton is bouncing around all over the place. The acidic proton is going to be in equilibrium with all of these species. All that really matters is we eventually get the proton on the carbonyl to protonate the carbonyl. How exactly it gets there, it probably doesn't matter all that much. That's why I'm choosing to present it in the same way I present other neutral nucleophiles, so that we have the same story to go off of. Why would we protonate a carbonyl like this? To make it more electrophilic so that even a neutral nucleophile can attack, and that is the next step. The neutral nitrogen attacks the carbonyl to do the nucleophilic addition and bring the amine into the product. That forms our tetrahedral intermediate. This step is also in equilibrium. The nitrogen that we just added in is the best leaving group in this system, and it could easily leave to reform the carbonyl. And that's kind of part of the problem with where we are right now. The group that we just added in is the one that's the best leaving group. But I don't want it to be the best leaving group. I just went through all this trouble to add it in. I kind of want it to stay. So we need to do what I call the proton shuffle. We need to take the proton off of the thing that we want to stay and put it on the group that we want to leave. We'll do that in 2 steps using more amine solvent as the shuttle. The proton shuffle sets us up for part 2. We've taken the proton off of the group that we want to stay, and we've put the proton on the group that we want to leave. Now we're ready to do part 2, getting the water out. To do that, we can drop a lone pair of electrons down from nitrogen to form a carbon-nitrogen double bond, and that will kick out water as a leaving group. That leaving group expulsion step is also reversible. Water is a weak nucleophile, but it can attack this carbonyl because it is positively charged and activated. All that's left is to neutralize the charges, fill out some paperwork to get to our final product. If you're not familiar with me talking about proton transfer steps as paperwork, watch my paperwork video that I've got linked down below. To do the final proton transfer to the end, we'll use more amine solvent as the base to take the acidic proton, both because it's statistically the most abundant and because it's just the strongest base in solution right now. And that will deprotonate our imine product and form the final product of this reaction, the imine that we have been trying to form the whole time. This last step's an acid-base step. It's also reversible. This for acid-base equilibrium is reversible, favoring the products. We have a protonated nitrogen on both sides, but the one with an sp2 hybridized nitrogen is going to be a stronger acid, and the sp3 hybridized nitrogen, not drawn here, is going to be the weaker acid. While I'm here, let me stress the importance of this last step. In order to do this last step, we needed a proton attached to this nitrogen. The only reason we have a proton left on this nitrogen is because we started with a primary amine. Had we started with a secondary amine, there would be no protons left on this nitrogen, and we would not be able to form an imine. Instead, we would have to do something different to form an enamine, and I have a separate video on enamines that I'll link to down below. The last thing I'll point out is I want you to notice that every step in this mechanism is in equilibrium. Every step is either an acid-base step or in equilibrium. That means that this reaction is in equilibrium, going back and forth between the starting materials and the products. So how do we know which side will be favored at equilibrium? We'll use Le Chatelier's principle. Notice that the byproduct is water. In a lab setting, we can either flood the system with water or we can remove water from the system. If we remove water from the system, then that will drive the equilibrium toward the products. The fact that it's in equilibrium tells us that we could also start with an imine and add acid and water to go back to the carbonyl. In that case, we would flood the system with excess water, driving the equilibrium back towards the original carbonyl. This is our reaction card for the imine formation. The three-phrase sentence for this reaction is an aldehyde or a ketone reacts with ammonia or a primary amine to make an imine. We need to know that three-phrase sentence in all possible combinations. An aldehyde or a ketone reacts with a primary amine to form an imine. A primary amine turns an aldehyde or a ketone into an imine, and an imine is formed when an aldehyde or a ketone reacts with a primary amine. It really does have to be a primary amine or ammonia. With a secondary amine, we get an enamine formation, and with a tertiary amine, there's no reaction because there's no acidic protons to remove. And this is a completely reversible reaction. It's in equilibrium, and so acid and water can turn an imine back into the original aldehyde or ketone. This is a regioselective reaction. It only works for aldehydes or ketones. For other carboxylic acid derivatives, we don't form an imine. If it reacts, we form an amide. This really doesn't have any stereoselectivity to talk about. There's no new stereocenters in the product. And this is a redox neutral reaction. Both the starting material and the product are at the 1 CZ bond oxidation level.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.